This is an AQA Year 13 chemistry topic. We're looking at acids, bases and buffers, and this is part 3 in the series for this topic. So in this video we're going to take a look at weak acids and bases. In previous videos we've looked at calculations relating to strong acids and bases. So as always, I'm going to recommend that you have a go at the activities, pausing as you go, get to see what you can do and what might need a little bit of time and attention. So, as I've said, we're looking at weak acids and bases. We've got some objectives here. We're going to be able to define what those terms mean. And then we're going to introduce some new calculations that are going to build around some of the expressions that you've already hopefully become familiar with. So let's start with the definition of a weak acid and a weak base. And actually, the definition for both of these is the same. I'm going to give you two choices that commonly get written down. One of them is correct. One of them would not get you marks in the exam. So you'll often see that people will write down does not fully dissociate in solution. You'll also see only partially dissociates in solution. The top one will not get the marks. The implication is that it almost fully dissociates, and actually the equilibrium lies much further over to the other side. There's only a small amount of dissociation with weak acids. So the definition that you would need to write down for either a weak acid or a weak base is that they only partially dissociate in solution. Okay, let's move on and let's look at another K. So we've done rate constant K, we've done Kc, the equilibrium constant, Kp, the pressure constant, Kw, ionic product of water, and now we're introducing Ka as well. And it is related to Kc. So write out the expression for Kc for this reaction, the dissociation of Ha. And as always, it's product over reactants. We've got our square brackets to represent concentration in moles per decimeter cubed. Now, in the case of dissociation of acids, we give the symbol Ka instead of Kc. So it's a very specific form of Kc. And we've got some Ka values here for the dissociation of 4 acids: chloroethanoic, benzoic, hydrocyanic, and ethanoic. So your first task here is to really think about which of these has got the highest level of dissociation, which has the lowest, and how would you explain that scientifically? Well, let's begin by once again writing out the expression. We've got Ka now, H plus times A minus over Ha. Now, if we dissociate more, that means we're going to get more of the dissociated ions, and that means the number on the top line becomes bigger, the number on the bottom line becomes smaller. So the greater the dissociation, the greater the Ka value. So the strongest with the highest Ka value is chloroethanoic, 1.3 by 10 to the minus 3, and we have got hydrocyanic, much smaller, 4.9 by 10 to the minus 10 is our weakest, and the other two sit in between, and you can work out the order of all 4. So let's now start to build up towards the calculation. In a sample of ethanoic acid, if molecules dissociate, what assumption could we make about the concentration of the ethanoate ions that we get and the hydrogen ions that we get? Well, if we consider Ha breaking down into H plus and A minus, let's say that I have 1 mole of Ha. If I break that down, I get 1 mole of H plus and 1 mole of A minus. If I had 10 moles of Ha and I dissociated them, I'd get 10 moles of H plus and 10 moles of A minus. Crucially, the H plus concentration is equal to the A minus concentration. That's going to be really important moving forward. So how could we use that information to simplify the expression for Ka so that we don't have any ethanoate ions in there at all? And for ethanoate ions at the moment, we're using A minus. It's really important to note that when you do this, this is not the expression for Ka. This would be wrong. You're only going to do this simplification if you're working out the pH of a weak acid. But let's take a look. Ka is H plus times A minus over Ha. If H plus equals A minus, then we can take the A minus out and we can simplify and say H plus squared. So Ka is H plus squared over Ha. We're going to use that as we go through the calculations. So there is a worked example here for working out the pH of a weak acid. I'm going to recommend you pause, have a read through this, but then there's going to be a few opportunities for you to do some calculations of your own. Okay, so let's start with the left-hand calculation here. Give it a go, see how you do, and then you can review. Now, the first thing, I'm going to write out the expression Ka is H plus squared over HA. Remember, that's not the expression for Ka. It's the simplified version that you can use in this calculation based on the assumption that we're making. Now, let's rearrange it. H plus squared is Ka times concentration of HA. Now, we want H plus if we're working out pH, so let's simplify. Concentration of H plus is the square root of Ka times concentration of HA. Remember, this is the concentration of the acid. So what I can start to do now is substitute figures in. I've got my Ka value provided, 1.3 by 10 to the minus 3, and multiplying by my concentration of chloroethanoic acid. That means we get an H plus concentration of 1.61 by 10 to the minus 2 moles per decimeter cubed. Once I've got H plus concentration, I can find pH by substituting into the expression for pH. And in this case, we get a pH of 1.79. So have a go at the next one if you haven't already. Cutting a few steps here and I'm getting to the expression that's going to get us to concentration of H plus, root Ka times HA. And I can put the figures in and I've colour coded them so you can see where they've come from, my Ka value here and my concentration here. And that takes me to an H plus concentration of 7.94 by 10 to the minus 3. Substitute that into my expression for pH and I get a pH here of 2.10. These are reasonable, they are definitely pHs of acids, they're below 7. Couple more examples for you to try and then we'll review them. So once again, concentration of H plus is root Ka times HA. Colour-coded the figures to see where they're coming from, and that takes us to an H plus concentration of 4.12 by 10 to the minus 4 mole dm to the minus 3. If I substitute that into my expression for pH, this standard that comes up in so many of the calculations, we end up with a pH of 3.38. And finally, the hydrocyanic. I've gone straight to the expression and put the figures in, colour coordinating them so you can see where they've come from. I get an H plus concentration of 5.73 by 10 to the minus 6 moles per decimeter cubed. Substitute that into my pH expression and I get a pH of 5.24. Now it's a very low concentration and it's a very weak acid. We know that because it's got such a low Ka value there. So it makes sense that the pH is going to be much closer to 7. Just to finish off on this video, we're going to introduce pKa. This is an extra little calculation that can be done, and it follows the same principles as pH. So where pH is negative log to the base 10 of the concentration of H plus ions, pKa is negative log to the base 10 of Ka. So have a go at working out the pKa for each of these four based on the data in the table. It's as simple as putting the Ka value into the pKa expression. I will get a pKa of 2.89 for chloroethanoic acid. For hydrocyanic, I get a pKa of 9.31. For benzoic acid, I get a pKa of 4.20. For ethanoic acid, I get a pKa of 4.77. So one last question just to finish off. What is the trend in pKa values as acids get stronger? And what we can see, and I've brought the data over here so we can look at it again, is that as the acids get stronger, and we've already established that chloroethanoic was the strongest of the acids and hydrocyanic was the weakest, the pKa gets lower as the acid gets stronger. So that takes us to the end of part 3. Thank you for listening and goodbye.